I worked for a long time on kind of gauge theory in strong background fields, mostly in QED. And then more recently, I started working on Yang mills and gravity, also in the presence of strong external fields. And I'll explain what I mean by this as we go on. I realize that, let's see, many of you are senior and probably know more about some of this stuff than I do. Some of you are postdocs and some of you are PhD students, and I'm going to hopefully aim this at a level where the PhD students can get something out of it at least. Yeah, right. And I'm sorry if you get bored, because I realize that I actually collaborate with 40% of the speakers at this conference. So, all right, so let's get started. Some motivation. I'm going to talk about amplitudes in the presence of strong fields, so I should tell you what I mean by strong fields. What I've got in my head is that there is a flux of either photons or gravitons or gluons. I won't talk much about Yang mills. So there's some flux of photons or gravitons, and huge numbers of them coming in, participating in some interaction. So many of them that we can basically ignore the fact that some of the energy they provide is going to be eaten up during the interaction. So I'm going to be neglecting depletion. And again, we'll see exactly what I mean by this. This is what. No, never mind. Right. So the way you should think about this is that rather than scattering particles off particles, I've got a bunch of particles and I'm going to scatter them off what is essentially some kind of classical field, maybe coming from very intense laser, or maybe we're scattering off some kind of background, some kind of curvature, right? And this field of this curvature is so strong that it doesn't change itself during the scattering process. So where do you find such fields? Oh, astrophysics. So in magnetite environments, right? You've got magnetites with these huge, strong electromagnetic fields. There you go. Your first bunch of references. Future colliders might require you to take account of strong field effects. If I've got very dense bunches of particles and I throw them at each other, then the particles in one bunch will feel the collective Coulomb field of the other bunch, right? And you can't just ignore this, and you can't treat it perturbatively. It's such a strong interaction. Terrestrially, some of the strongest electromagnetic fields. Ooh. The strongest electromagnetic fields you can make, and which are in some sense controllable, are in intense lasers. And of course, many of you are interested in. Right, you can imagine that there are regions in the universe of extremely high curvature, and we are, putting a sci-fi hat on. We're there at this region of strong curvature, throwing particles at a black hole or something else, and looking at scattering processes in the presence of this curvature. Okay. But why should you care about this? Well, it's keep it stuck in here with me for the next 2.5 hours, so you don't have a choice. The simple and most obvious example is consider the case of extreme mass ratios. Right, so I've got some great big mass there, smaller mass there. These guys are interacting. Maybe we're looking at an in-spiral, the start of an in-spiral. And in the regime that one mass is very much larger than the other mass, then this particle here only sees essentially the Coulomb or Schwarzschild field of the heavy mass, and that's what it interacts with. So that little mass sees the field due to big M. Okay, and there's the hope that future gravitational wave observatories will be able to, through studying in spirals and other events, will also be sensitive to things like the curvature of the universe. And there's some background curvature. It's not particularly strong in some sense, but you know, it's there. It's a background. It's something which is fixed and not changing by the fact that we're doing our scattering experiments, right? So future observations might be sensitive to that. Other reasons to care. When we're talking about strong fields, what I really mean is, in some sense, there is a coupling in the game, which in appropriate units, made dimensionless, exceeds unity, right? So I've got some coupling which is larger than one. Perturbation theory, just out the window. So you've got to use non-perturbative methods, and at the same time, you're going to get access to kind of non-perturbative physics. So that's cool. Also, you can't read my handwriting, do tell me, because I know it's terrible. These kind of effects can be seen, right? Terrestrially, we can go out and do measurements which can observe non-QFT effects. So review in 8 and in 12, there's the experimental results from a few years back. Again, this is coming from like the QED laser site. Other reasons to care. So the Amplitudes program, all the cool stuff you know about Amplitudes, double copy, unitarity, recursion relations, you name it, whatever you like. If those are like fundamental properties of gauge theories and gravities, then they should hold not just in like perturbation theory in vacuum, right? They should hold, for example, doing perturbation theory about any background. Playing with these, playing with these strong fields, they provide you with a background. It's a good way to test whether these nice amplitude results generalize or how they generalize and so on. This is a hard topic, I think. There's not a huge amount. Well, there's some results, but not a huge number. Okay, hard. Yeah, please. Yeah.
Amplitudes are usually asymptotic observable.
Yeah.
So they are sensible only to the asymptotic of the space-time, not to what's happening inside.
Nah. You measure them asymptotically, right?
Yeah.
But I mean, just think about a 3-point amplitude. What does a 3-point amplitude look like? Got that. Right. D4x, integrate overall spacetime. Interaction happens somewhere in spacetime. You integrate to go and get amplitude, you integrate overall.
Yeah, but you kind of integrate, like what's happening in the bulk is not really sensitive to, like the amplitudes kind of average what's happening in the bulk. And then whatever you measure asymptotically.
You measure asymptotically, but what you measure is very much a function of what happened in the bulk.
Yeah, I agree with that.
So,
The thing is that if you put a background and you sum over all the, and you sum all the quanta, then it's just the same thing. Having a background is just resumming some perturbation theory if you have a background in the part.
yeah, it is. Right, okay. Of course it is. But the point is, if that background is like strong in some sense, then you have to resum. Even typically you can't. Right? So if you just say, oh, let's do perturbation theory, because I know that if I resum it, I'll get the right answer. Well, you do like first order perturbation theory or second order perturbation theory, you're going to get absolute nonsense.
Well, I just was asking about properties. I mean, those properties is just non-perturbative of these unitarity properties are non-perturbative. I was just confused by the statement. Well, what's true?
Yeah.
beyond.
Okay, absolutely. So yeah, unitarity doesn't care about perturbation theory or anything else that exists, right? But all the methods and the tools like integration by parts, double copy, how does it actually work beyond vacuum perturbation? That's the question, right? How do you get it to work? Or what do you have to do to generalize? Yeah, cool. Do ask questions, by the way. Right. Okay. Anything else? Yeah.
About this intuition of the flux of photon,
Yeah.
summation of perturbation theory. You can also get non-perturbative stuff in the if with these methods, right? It's not just resummation.
No. You can't get them to this stuff. We'll do an example explicitly later on. Very good. All right. Do we have a board eraser? Come on.
There's nothing there on that tray.
Get half a board out. Yeah, okay. All right. So. Practically, what kind of calculations are we going to do? Hey, just. Picture that we have is we've got some particles coming in. And we want to scatter them off this flux of photons, or we want to scatter them off some kind of background metric. How do we describe it? So if I think of like scattering off some kind of classical field, right? Normally we describe scattering, particles that we scatter as number states. Fine. You can't describe classical fields that way. Right. If I just take the expectation value, some number state n of either my gauge field or oops. If n is a state of n photons or n gravitons, I take the expectation value of A, the potential, or I take the expectation value of the metric, the graviton perturbation rather, I get 0, right? Number states don't have any classical fields associated with them. That's dull. And the reason, of course, is just that, these guys are linear in the creation operators. So they change n to n plus 1, and that's 0. Done. Okay.
So the hat, what's the hat
Operator.
operator?
Yeah.
Okay.
Yeah. So actually, just to get the notation fixed, e to the minus x. So mu. Down again, that's got some spin. That's got some spin. It's not dagger. So there's the mode expansion for A. That's the on-shell measure. That's what OS stands for. Exponential polarization. S is some spin or helicity, whatever you want to call it. And for the graviton, it's exactly the same, of course. If I use a helicity basis, then I can just double copy the polarization tensors. Yep. Happy with that? Yeah. Okay, good.
Excuse me.
Yeah.
The number states, those are number states for this other field that you're drawing there?
Yeah, exactly. So let's think of, when we do scattering, these guys are going to be number states. I'm going to throw in 5 particles, right? But these guys are not going to be number states. So let me tell you what they will be.
What kind of space-time do you have in mind?
Okay. So for QED, it's flat. Everything in flat space-time, but there is a background field. And for gravity, the background I'm thinking of is something which is asymptotically flat. because otherwise it gets a little bit hard to define what I mean by scattering. But tomorrow we'll get on to the case where it's maybe not asymptotically flat. And there's a bit.
I'm just worried about situations where numbers fit and fine.
Okay, good. So I'm definitely thinking about the time. At the minute, everything is initially flat. So I can define number states, not a problem. There's no ambiguities.
Thinking about some static space-time anyways.
No, I'm definitely not thinking about static space-time at the minute, because that wouldn't be.
So these are asymptotic numbers.
Yeah, absolutely. Yeah. Good. How do we describe these classical fields? This is how we describe the initial state for our scattering. Our scattering thing. Fields. Call these guys Z. Given by some operator. D dagger acting on a vacuum. D dagger is of course the displacement operator, which creates coherent states. So that is the exponential. Z. It's got an S, that's got an S. Everything's got an S on it. Let's be nihilistic. I'm going to start dropping it very quickly. Right. Yeah. So this guy is a displacement operator. If you've never met this guy before, many of you have, I know. There's a nice textbook on quantum mechanics, quantum optics, in fact, which introduces coherent states and all these kind of things. So you let this guy act on the vacuum, and what you get is something which looks like K, A down K, 0, and there's some normalization factor. So you stare at this and you expand the exponential, then of course this guy is vacuum plus a 1 photon or graviton state plus 2 photon or graviton plus 3 plus 4 in some superposition. Is it coherent state? And the point is, if I now calculate the expectation value of my field operator, be it A or H in this state, and what you get, well, the annihilation operator acts on this guy as a derivative with respect to a dagger, so it just brings down a Z. And of course, what you get is just dk. One shall get e to the minus I, k dot x, I get epsilon mu s, z s, okay, plus complex conjugate. And if you go through it and put all the h bars back in, you will find it is a classical field, right? If you get all the h bars right. And if you want to do that, it's in 19, which is donal. Coherent states are nice. Their states are minimal uncertainty. Ah, well, that certainly sounds classical, right? Good. And there's lots about coherent states in those papers. There. Okay, so coherent state has a classical field associated to it, right? I haven't said anything yet about whether or not this field is strong or weak or anything. No. We will get there. Any questions about that bit? Let's put it all together. my initial state is going to be the coherent state of stuff. And I'm going to ruin my own notation now. I'm going to write my initial state like that. Okay. By this guy, I just mean number states of particles. And by particles, I might include E, gamma, G, electrons, photons, other gravitons, whatever you want. And this is my coherent piece. This is my field. Yeah. And there's something slightly subtle to think about in that definition. I'll come back to it later. Good. Let's calculate something.
What was the name of, sorry,
This is the scattering you're considering here. This is right here is. Switch.
Yeah, so I'm just being really rubbish notation day. So my in state is that guy. Sorry. Yeah. Absolutely.
what was the name of your D operator?
Displacement.
Displacement. So
See
if
why.
the displacement operator acts on the vacuum, you get a coherent state.
Yes.
What you say is, I have an in state with some particles, and then I apply the displacement on this,
Yeah.
and that will be the in state that you consider for
Yeah.
your.
That's fine. Absolutely. So I've forgotten how to spell. Observables. All right, I've got an in state. What do I do with it? Well, I evolve it in time with the S matrix, right? And then I use it to calculate some expectation value. So, let's call that Z in, right? For reasons that will become clear shortly. Okay, so I take this state. I evolve it in time with the S matrix, that's S. Okay, and I want to calculate the expectation values from observable. Why do I want to calculate an expectation value? Well, it's because they have a nice H bar goes to zero limit for one reason. Yeah, and of course, we're interested, general relativity people, in GR stuff from classical limit of QFT amplitudes, right? So these guys have that classical limit. How are we going to calculate it? We're going to insert one written in a clever way. Okay. So what would you normally do? You're doing a bog standard QFT perturbation. You'd write one, right, as a sum of number states. Yeah? You'd stick it in there. And then you would have like F, S in S matrix elements, and you would calculate those in perturbation theory.
Sorry, just
Yeah.
I'm getting something stupid.
No.
Confused. So right now I have in mind photons and some other field. Right?
Yeah.
This S matrix is an S matrix for the combined system.
This is just the ordinary bog standard S matrix of the combined system of QED
Combined system.
or gravity or Yang-Mills, whatever you want.
I mean, for your photon and the other field.
Yeah, for everything. Yeah, absolutely. So yeah, S is like the full S matrix, whatever QFT you've decided to look at. Yeah. All right. So this displacement operator is unitary, so d dagger d is 1. Right, so I can do that. That's trivial. Right. And then that 1, I'm going to write as my usual sum over minus 6. Right. Sum of F, D, Z. Right. Just think of this as the bog standard sum over F, because it is, that you would normally use. So let's plug that in. Sorry. The expectation value. What does this give me? If I assume just for the sake of simplicity, right? That the operator I'm looking at, or the observable I'm looking at, has these guys as eigenvectors. So I just get a factor, you know, some function of the final state variable. So imagine it's momentum, total momentum, right? It's just to make the notation a bit, the expression simpler. Then this is what you get. Z in I've got got F. I've got my sorry, D bagger Z. I've got an S, and I've got my Z. Not squared. Absolute trash in my notes. Makes no sense. All right. Okay, what is that? That's a bit of a mess. This bit. I'm ugly and weird. Can I kill this? Right, this is the important bit.
RDF, the basis of eigenstates for the observable.
In general, no, they won't be, but I'm cheating. I'm imagining that they are. Right. So if like this is total momentum, so and if I just plug in an ordinary expand, you know, a free basis of free states, then yes, it'll be an eigenvector. If they're not, then you get two sums over F and F prime, and it just gets messier. But yeah. Okay.
Sorry, probably it's irrelevant, but maybe it should be D and not D dagger, right? Because that's
Probably. Thanks, Carla. Good. Right. Well, what is that thing? Let's pull the D dagger out of the initial state. So it's just the amplitude bit or the overlap that I'm looking at. There's the F, there's D of Z, there's the usual S matrix, and then I've got a D dagger. Z acting on my thing that I'm pulling in. Maybe just a bunch of particle states, particle number states. Yeah. And then you have to use the following result. D of Z, A of K, D dagger of Z. So this is why the thing is called the displacement operator. So if you sandwich the creation and annihilation operators inside it, they get displaced by this classical field variable, which is appearing in the coherent state. And the same for A dagger with Z dagger. Yeah. And you can see that I've already started dropping the split label because I'm lazy.
One thing to.
Yeah.
So you're assuming that D commutes with it?
Am I assuming that D commutes with O? No, I don't think so. If you imagine stuffing the like the sum in there, kind of. Okay. There is a subtlety here. You're right. I'm imagining. Yeah, I am imagining that it's observable. Doesn't care about the field itself. Yeah. So this is like, yeah, it's measuring the particles which you scatter off the field or something. Good. Yeah. Sorry, that's subtle. Yeah. All right. Z is whatever appears in the coherent state. All right. So remember, so the expectation value of the field goes like e minus ik dot x. Well, Z. So it's like the Fourier transform of the classical.
So it is different if you apply the displacement operator to the in-state. Like the in-state is created by some A.
Yeah.
Is it different if you Like if you first create the background and then
Precisely. So that's the subtlety with this, but from a scattering perspective, it's okay, right? Because you would never say, okay, I'm going to scatter, so some photons off some other photon off a laser, and I'm going to align them next to each other and put them in co-propagating, right? You would never do that because it doesn't make any sense, right? You would collide them. So like the coherent state and the particle number states of scattering occupy different parts of the space. So there's no ordering. Good. You good? Right.
Is that the depletion assumption that you were making at the beginning, or
No,
that the
no,
commit
no,
later
no,
on?
we are about to make that assumption. We'll get there. Okay, so what's happening here? Everywhere in the S matrix, so there's an A creation operator, right? An annihilation operator. It gets displaced by Z. Or Z dagger. So this combination DS D dagger is exactly the same as the usual S matrix, except wherever it depended on A or H, right? It now gets displaced. And because the S matrix is the exponential of the interaction Hamiltonian, really, wherever you see like EA, your original action Hamiltonian S matrix, that gets displaced by a physical field. It's a classical, it's just the Fourier transform. That's it. QED, we do gravity, then if you had eta plus kappa H for the graviton perturbation, then that will now get shifted to kappa some classical. That's all the displacement operator does. It just shifts the field by classical. So what this is telling you is that, up to caveats about quite what this operator is, what you're really calculating, or rather observables that you're interested in calculating, come from, come from an action in the background field. Yeah, that's the field. So here's the depletion or no depletion assumption that we started with. All I've done is shoved in a particular expression for what? For unity, right? That's an exact statement. Now, so depletion is in there, back reaction is in there, radiation reaction, cell force, whatever. It's all in there, right? But how are you going to calculate these things? And what does it look like? It looks like, and these are number states, this looks like perturbative scattering on a given background, right? And that's how you calculate it. The background is fixed, it is that field, right? And then you do perturbation theory on that background. I'll make this a bit firmer on the next blackboard. Right? The depletion is in there, back reaction is in there, but it basically requires resumming perturbation theory in the background, which is tough. See, so just by saying, okay, I'm now going to calculate these in background field perturbation theory, that's where you're saying I'm going to nick the negative depletion. I'm going to shove it to high orders in perturbation theory where I don't worry about it.
Excuse me.
Yeah.
Sorry, I keep asking the same question, but these two equations correspond to scattering by either the photon or the graviton.
Yeah.
Now the Z labels these asymptotic states
Yeah.
that you're putting in, but the scattering is by something inside the bulk, as you say, right? But if you write it this way, it makes it look like you're considering the bulk field also as Minkowski plus the perturbation.
Yes.
The kind of space-time you'll be considering.
Yeah, except what we're going to do. So, where is it? So, these in a terrible order. So eta plus this background, just this particle field bit, that's what I'm going to consider to be my background metric.
Mhm. It's
And
a-
I'm not going to consider that bit perturbative. Consider that as fixed and given, I just have to deal with it.
Space-time manifold and usually R force.
Second?
The manifold is just R force. Is that right?
Yeah, well,
This way. look.
that's right. That's right, there. It'll be, it might become clearer in a second. All right. Okay. So those amplitudes over there on the right. They come from a theory with Lagrangians like this. So if it's QED, that's already written. Wherever you see EA in the action, you just replace that by EA. That's EA classical. That's it. Gravity, Einstein-Hilbert, coupled to whatever matter you want. Okay. If you would normally write that to do perturbation theory, you know, Minkowski plus graviton perturbations. You now shift that guy exactly the same way. Sorry, my K's look like kappas, I realize. Oh God. Confusing. Those are kappas. All right. And this guy, I think of as my background metric. Right? Yeah. So gauge theory, I've just got some external field in the game. Gravity, I've got some given metric, and then I'm looking at scattering on that metric, or I'm looking at scattering in that field. Okay. Great. I've given you the Lagrange.
You are rephrasing the background field method with the displacement operator in the side.
Yeah, so we start with coherent states. You've turned it into a background field. That's it. That's all it is. The coherent states are background fields. Full stop. Okay. So I've given you the Lagrangian. You can just go away and calculate. Right? I still haven't said anything about this field being strong. So that's the question to answer. I realize I'm being slightly vague about what I mean by strong.
Can I ask you?
Yeah.
Can I take any space-time that is asymptotically flat and write a coherent state?
Right. So, excellent question. Let's start with the coherent state, which is an on-shell thing, right? It's made up of on-shell photons. So this eta plus kappa h will obey the linearized Einstein equations, vacuum solution. If you want to, but I mean, once you know that that's how you put a background field into the game, right? Well, then you just ignore that. And you just, you know, if I want any gauge field in there, I'll just add it into the action. If I want any metric, I'll just do scattering on that metric. You can make this a bit more formal by allowing for like kind of virtual coherent states, which Ricardo might say something about.
Yeah,
Yeah.
maybe.
You will now. Yeah, so you can generalize it to like off-shell coherent states if you like.
Any background be written out. And any background you want originate from a coherent state.
If it's a vacuum solution, in QED, yes, full stop. If it's linearized vacuum solution in gravity, yes. And of course, some full solutions will also be coherent states. Well, shoot. That's a coherent state of virtual gravitons, yeah, linearized, yeah. But they have to be virtual because it's got a source. It's not a coherent state of real graviton. Yeah. So let us write down. So, you know, start off with coherent states. We've got the mode expansion, which has like, you know, looks like an on-shell field. It creates on-shell states. They correspond to vacuum solutions. Terrestrial is not its constants. So strictly, you need to kind of mess around a little bit with what you mean by these coherent states if you want to describe terrestrial. It can be done. You have to go off shell a little bit.
What do you mean by a source for terrestrial? You mean the singularity or what?
I mean, this guy kind of thinking about terrestrial, so naked synchronous.
Oh, what's the source? Or what do you mean by the source?
Just one particle. Sat theology.
Oh, okay.
Yeah.
Just think of instead of the linearized Churchill, shifting eta plus kappa to kappa can just shift
exactly.
Churchill to a non-linear
Yeah, precisely.
classical field.
Yeah, absolutely. So like, once you know how this works, you just go, oh, fine, I'll just choose this to be whatever I want. Then off I go. I go and calculate it. Yeah.
Then that with Stephanos' question, it doesn't have to be linearized.
No, the question was, can I express it as a coherent state? And that's less obvious.
Like you cannot find a coherent state for a non-linearized.
Yeah. Exactly. You can in QED because photons don't interact with cells, right? Gravity you can't.
Yeah, but I'm sure it's possible.
We might get to it.
Is there a reference in your notes about this?
No, but there is a slide coming up. I'll kind of sketch it on the board. I'll find you a reference. All right. Good. Where do I get to? Yeah, right. Okay. So how do we treat this field as strong? If the coupling to this field is somehow larger than 1, we don't want to treat it in perturbation theory. How do we do that? Let me illustrate QED. Just because I don't have to write out messy Einstein-Hilbert stuff. Right, so here's our Lagrangian. It's minus a quarter f squared plus I psi d slash plus or minus a slash c a classical minus l. So, right. Happy with that? Good. All I've done is wherever there was an EA before, I've shifted it by this classical field. Now I'm going to do something completely trivial, which is just to write the terms in a different order. Yeah, brace yourselves. Okay. So this is minus a quarter f squared. And then I'm going to do plus psi bar d slash minus tell you what that is in a second. Minus e psi bar psi. And what do I mean by d mu? I just mean the background covariant. So the covariant derivative with respect to a classical, right? That's what the curly d means. So what is this? There's your usual photon propagator. Nothing has changed there. Oh, that should have a sign in it, sorry. What's that? If that was an ordinary D, then that would just be, an ordinary propagator, like that. But now it's this background covariant derivative. And of course, the background field or the classical field is a function of time. So that is a complicated operator. Its inverse we draw with a double line, just to remind ourselves that it is not the free. It's not the free kinetic term. Yeah. Happy with that? Okay. And what's that? Well, that's just the bog standard vertex of QED, right? There's nothing special about that. That is just one photon, right? I've got to draw a double line because it's these propagators that connect at the vertex, but that's it. So the expression for that vertex, there's the diagrams, what's Feynman rules. That guy is just minus IE gamma mu, as normal. That's what the vertex is. This is just your usual G mu nu, whatever gauge you want to put it, right? And this is what it is, right? There is no expression for this in general. It's just the inverse of that operator, and that's all you can say. So you've got
Think naive.
second.
Why do we not replace the A and the F field strength? Is it something to do with the coupling? Or?
Yeah, it's because the displacement operators act on the interaction Hamiltonian. The interaction Hamiltonian only sees the interaction bit, right? All the free stuff is stripped away. That's why you shift this.
But I think it's because this term would you replace with the F, it's a total derivative, I think.
It would be total derivative anyway. If you shifted this for a vacuum solution, it becomes a boundary term, it dies.
So you actually replace.
Yeah, but that's just a constant. Who cares? Throw it away. Good. Good. All right then. So those are your Feynman rules for background field perturbation theory, or the Fourier expansion, as it's sometimes called.
No.
Yeah.
That's the classical field transform under gauge transformations.
Yeah.
Is it not?
No, transforms it is. I feel. Yeah, but you can play a lot of like dirty games here. So I mean, if you want to, you can choose your back. So you're going to gauge fix, obviously, at some point. Your background field can be in a different gauge if you want it to be. It's not gonna.
You can choose different gauges.
Yeah, you can choose different gauges. People do. But what I talk about, for all the situations where this expansion is actually useful and realizable, then the fields that you're going to be using are so simple that basically, this gauge is whatever gauge is the other gauge. It's all the same. So it's like, yeah, but it does transform. Okay. So this guy is in general complicated. Right. We'll invert this operator to find out the problem. Okay, what else do you need to go away and start doing calculations? The only other thing that you need is to know how to do the external legs. Yeah, but that's given to you by LSZ. So LSZ comes along and says, do something to this propagator. Things that you glue on are not just e to the I p dot x for an external leg. You glue on solutions of the background coupled to evaporation. Just generalizing what you would do in vacuum. Or the gravity, 1 over root g, d nu. Yeah, solutions of the wave equation in your background metric. Yeah, for scalars. Not big. No. Yeah. Get it? Right. Feynman rules, wave functions, go. So what this expansion is doing, right? It's treating to the coupling to the background without any approximation. I'm not expanding that bit in perturbation theory. This guy, I'm going to treat in perturbation theory as normal. This is scattering the particles on the background. Yeah.
There are also gauge fixing terms that.
Yeah, I'm not writing down the gauge fixed terms. You're absolutely right. Yeah, and ghosts and whatever else. Yeah, being really lazy.
Modification. Such kind of not.
It's basically this statement saying this is how I'm going to do my calculations. Right? So just look at the way this is set up. It's like the background is inside this bit, inside the propagator. That's the only place that it appears. But that is a given classical field, right? Which came from a coherent state. This is perturbation theory. So this is just number states scattering on that background. How are you going to deplete like a coherent state, which has an infinite number of creation operators in it, by just doing like 4 or 5 particle scattering? You're not going to see it. Picture. So if you calculate in this picture, depletion is in there, but it's in the resummation of perturbation theory. So it's very hard to see. Yeah.
In that last equation, those are technically covariant derivatives, right?
Here.
Yes.
Yeah, it's a scale of those.
Yeah, but if I wanted to do spin states, I need covariant with the background fields.
Yeah, absolutely. It'll just be the equations of motion which follow from the ground, just all be covariant. Absolutely. Yeah. Okay. So the obvious, like, kind of practical limitation of this idea is that if you want to treat the background exactly, you need to be able to write down this thing exactly, right? Which you can't do in general, unless, say, your field has a high degree of symmetry. And I'll put exactly in there. If you don't want to expand in the coupling, maybe you've got some other approximation which will let you calculate this in some real, some useful regime. So, some examples. Oh, I can't spell spatial. So the example of like scattering on a Coulomb field or scattering on a Schwarzschild or linear Schwarzschild background is, of course, old hat. It's a nice recent paper by Luke. No, not in the room, where he talks about these wave functions. So when I say wave function, by the way, I'm going to mean like solutions of like part of the theory. So the external legs. Shock waves, which we will talk about later today. Engaged theory and gravity. They're nice. You don't know what a shock wave is. We'll talk about it later. 36. And plane waves, which I'll talk about next lecture. Okay. So in those situations and others, you can write down this propagator exactly without approximation in the background. You can go away and start doing your calculations. So in the last 5 minutes, good. Let me just, and this will answer, I think, at least one of the questions from earlier. Let's just write down the diagrams for a few processes that you might want to calculate. And this is where things start to look a little bit different. So, first of all, 0-point amplitudes. That guy, vacuum bubble, is not trivial anymore. It's not a phase. This is the problem with these background field things. All the diagrams that you would normally just ignore turn out to actually be quite important. So this guy describes vacuum decay. We will do that tomorrow. 1-point amplitudes are not trivial either. So in QED, I could draw this. And in gravity, let me draw. Right, that's supposed to be a graviton. Right, let's do QED. So what is this? This is a 1-point function where a photon suddenly appears from nowhere. Yeah.
Time to break.
Oh, yeah, I know, I'll get there. The physical picture going on here is that you have some electromagnetic field. Let's say I've got 2 lasers, right? And I collide them. What happens classically? Nothing. They pass through each other. Quantum mechanically, they will interact. The photons will scatter. So they'll generate photons which are not part of your configuration. And that's what this guy is describing. Purely quantum effect. Gravity, this will happen at tree level, right? Imagine that I send in 2 coherent states of gravitons, they interact, right? So whatever profile, whatever Z I had for those gravitons initially, that will not be the same. It will change and it will evolve in time, and that's what this diagram. So for there, you can put H bar to 0, and you still have that guy. Right, so this is why, not any coherent state is going to describe a vacuum solution, for example. Yeah, it'll change. Yeah. Okay. So 2-point amplitudes are not trivial anymore either. What's that? What kind of physics does it contain? Oh, did I not mention participation?
Scattering on the given field.
Yeah, right, it's just elastic scattering. You send the particle momentum P, it comes off with momentum P prime. Okay, GD6. Yeah, well, I see it. I think, yeah, we'll see it later on, right? So all the information about geodesic motion is contained in that diagram. So, I could also draw things like this. Right. Sorry, I probably should have said I'm a freak, so I draw all my Feynman diagrams from right to left. Sorry. Right, so what's this? This is electron-positron pair production. Right? An external field will produce pairs. Yeah. So nothing, 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 nothing. Oop, pair appears. Propagates out to infinity. That's not zero anymore. And stuff like this. Well, that's a familiar one, right? But you can have things where photons just change helicity state, for example. So send two beams of photons to each other with definite helicity, they'll come out with another helicity, right? Due to interactions with virtual stuff. So all these 2-point things are not trivial. 3-point diagrams are not trivial either anymore. So that P, K, P prime, and maybe that's a photon, maybe it's a graviton, doesn't matter. This is not trivial. It's not zero as an amplitude. The reason being, all right? Reason being, so the propagator, right, is now some very complicated function of x and y. What you've lost is momentum conservation in some direction, because your background is your flux of photons or gravitons is throwing in a huge amount of energy. It means you don't have overall momentum conservation. It also means that you can't really calculate these things in momentum space. There's no practical realization of momentum space because everything's a very complicated function of x. Even a position, so even at tree level, at 3 points in an external field, there's none of this rational function of kinematic data results anymore. These things would be arbitrary functions. Bessel, Airy, Whittaker, whatever you want. Right? You can get anything at tree level. And then after that, of course, 4 points, 5 points, etc. All right. Okay, sorry, I overran by a minute. I'll stop there.